Step outside tonight and look up. What you see is light, stars, the moon, the faint smear of the Milky Way if you're far enough from a city. Points of brilliance scattered across the dark in every direction, giving the impression of a universe that is, at minimum, reasonably well lit. A universe that burns, a universe that glows. That impression is wrong, not slightly wrong, not wrong at the edges where the data gets uncertain, wrong in a way that is so total, so complete, so geometrically absolute that once you understand it correctly, looking up at that star-filled sky will never feel the same again. Because what you are seeing when you look at the night sky is not the universe. It is the exceptions, the rare, isolated, statistically negligible accidents of heat and light that flicker in a darkness so vast, so deep, so permanent that the word dark does not come close to capturing it. The darkness between the stars is not like the darkness in a room with the lights off. It is not like the darkness of a forest at midnight, or the darkness at the bottom of the ocean. It is the darkness of genuinely, structurally, mathematically empty space. Space that has been empty not for years, but for billions of years. Space that will be empty not for years, but for trillions of years. Space that occupies, and this is the number that changes everything. Not most of the universe, not the majority, not the overwhelming bulk, all of it, nearly all of it, every direction, every distance, every scale at which you can possibly think about the cosmos. The warm, bright, life-sustaining exception you are standing on right now. This planet, this solar system, this galaxy, occupies a fraction of the universe's volume so small that expressing it in ordinary language requires stacking qualifications on top of qualifications until the number loses all connection to anything the human mind can hold. And it gets worse, because the darkness is not static. It is not a fixed backdrop against which the light performs. The darkness is expanding, growing, winning, and winning at an accelerating rate that means the bright exceptions are getting further apart every second, receding from each other faster than light can bridge the gap, vanishing over a horizon that physics has drawn permanently across the sky. The universe is not becoming darker, it already is dark. The question is how dark, and the answer, when you follow the physics all the way to the end, is the most disturbing answer in all of cosmology. But before we begin, if space fascinates you, a like and subscribe means everything to us. Let's begin. Heinrich Wilhelm Olbers was a German physician and amateur astronomer who in 1823 posed a question so simple it sounds almost childish, and so deep it took more than a century to answer properly. If the universe is infinite and filled with stars distributed roughly uniformly through that infinite space, then in whichever direction you look, your line of sight must eventually intersect the surface of a star. Every direction, every angle, and if every line of sight terminates at a stellar surface, the night sky should be uniformly, blindingly bright. Not dotted with stars against a black background, a continuous sheet of stellar light, indistinguishable in brightness from the surface of the sun. Olbers did not invent this reasoning. It had appeared in some form in the writings of Johannes Kepler in the 17th century and Thomas Digges in the 16th. But Olbers framed it with sufficient clarity that it became known as Olbers' paradox, and it sat, quietly unresolved, at the centre of cosmology for over a century. The darkness of the night sky is a paradox. It requires explanation. And the explanation, when it finally came, revealed something about the universe that is far more unsettling than a bright sky would have been. But first, we need to establish what the universe looked like to the scientists trying to explain it, what they thought they knew before the modern era of observational cosmology dismantled those assumptions one by one. For most of human intellectual history, the universe was assumed to be eternal and essentially static. Stars existed. Space was filled with them. The cosmos had always been, and would always be, roughly as it is now. This was not merely a folk assumption. It was the framework adopted by Isaac Newton, whose gravitational mechanics demanded a static, infinite universe to avoid the problem of all matter collapsing inward under its own gravity. A finite universe would collapse. An infinite uniform one would stay in equilibrium. Albert Einstein, when he formulated his general theory of relativity in 1915, faced the same problem. His equations predicted a dynamic universe, one that was either expanding or contracting, never static. So uncomfortable was this implication that Einstein introduced a term into his equations specifically to force static behavior: the cosmological constant, a kind of repulsive energy term that would balance the gravitational attraction of matter and keep the universe in equilibrium. He later described this as the greatest blunder of his career. In 1929, Edwin Hubble, building on earlier theoretical work by Georges Lemaitre and observational work at the Mount Wilson Observatory in California, published measurements demonstrating that distant galaxies are receding from us. Not randomly, not chaotically, but systematically, with recession velocities proportional to their distances. The universe is expanding, every galaxy on average moving away from every other galaxy, carried by the expansion of the space between them. This single observational fact resolved Olbers's paradox at a stroke, or at least it provided the major contribution to its resolution. If the universe is expanding, it also had a beginning, a finite age. The Big Bang, approximately 13.8 billion years ago, and a universe with a finite age contains only a finite volume of light that has had time to travel to us. The observable universe, bounded by what astronomers call the cosmological horizon, the distance beyond which light has simply not had time to reach us since the Big Bang. The night sky is dark in part because we can only see a finite portion of what exists. Light from beyond the horizon has not arrived yet. But here is the crucial refinement. And this is where the true darkness of the universe begins to reveal its full depth. The cosmological horizon explanation is real. But it is not the complete story. Even within the observable universe, even accounting only for the galaxies and stars that are in principle close enough for their light to reach us, the night sky should still be far brighter than it is. The number of photons that should be arriving at Earth from every direction, based purely on counting the stars in the observable universe, is vastly greater than the number that actually arrives. Something is eating the light, or rather, the light is losing energy on its journey, and the mechanism responsible for that energy loss is not absorption by dust, not scattering by gas, not any kind of obstacle in its path. It is the expansion of space itself. When a photon of light travels across the expanding universe, the space it travels through is stretching. That stretching stretches the photon too, elongating its wavelength, shifting it toward the red end of the electromagnetic spectrum in what astronomers call cosmological redshift. A photon that began its journey as ultraviolet radiation, or visible light, or even X-rays arrives at us, after a journey of billions of light years through expanding space, as infrared radiation, or radio waves, or microwaves. Its energy diluted, its wavelength extended, its ability to trigger the photoreceptors in the human eye essentially destroyed. The universe is not just dark. It is dark because the light that fills it has been systematically drained of its energy by the expansion of the cosmos. The sky blazes, but it blazes at wavelengths we cannot see, in microwave frequencies, in far infrared, in radio. Our eyes, tuned to a narrow band of the electromagnetic spectrum, receive only the residue of a universe that is in fact awash in radiation, radiation that has been stretched beyond visibility. This is the cosmic microwave background, the CMB, the afterglow of the Big Bang itself, the relic radiation from the moment, approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely for the first time. Originally a blaze of light comparable in temperature to a stellar surface, it has been redshifted over 13.8 billion years of cosmic expansion to a temperature of just 2.725 degrees Kelvin, barely above absolute zero. It fills the sky uniformly in every direction. We cannot see it with our eyes, but every microwave detector, every radio antenna, every appropriate instrument we have built records it continuously. The universe is not dark. Our senses are inadequate for the universe that exists. But that is not the full story. Because the darkness of the observable universe, the darkness we do measure with our instruments across all wavelengths, is itself a far more profound and terrifying quantity than a simple energy dilution argument would suggest. When astronomers in the late 20th century began measuring the total energy budget of the observable universe, cataloguing the light emitted by every type of source across every wavelength, they arrived at a number that confronted them with an accounting problem that could not be resolved by physics as they understood it. The math simply did not add up. In 1998, two independent research teams studying distant Type 1a supernovae, stellar explosions so consistent in their peak luminosity that astronomers use them as what they call standard candles, reliable mile markers for measuring cosmic distances, published results that restructured the entire architecture of modern cosmology. The teams were the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University, and the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. Their independent datasets pointed to the same conclusion, a conclusion so unexpected that many researchers initially suspected systematic error rather than accept what the numbers were saying. The expansion of the universe is accelerating, not slowing down, as gravity would predict in a universe dominated by matter. Speeding up. The distant supernovae were dimmer than they should have been if the universe's expansion were decelerating under its own gravitational self-attraction. They were farther away than expected. The universe, in the billions of years since their light was emitted, had expanded faster than gravity could break. Something was pushing. Something was winning over gravity. Something with negative pressure distributed throughout the fabric of space itself was actively driving the universe's expansion to accelerate. That something was given the name dark energy, and its discovery earned Perlmutter, Schmidt, and team member Adam Rees the Nobel Prize in Physics in 2011. Here is what makes dark energy so deeply disturbing from the perspective of the universe's darkness. Dark energy does not just accelerate the expansion of the universe, it progressively removes galaxies from our observable universe. As the expansion accelerates, distant galaxies recede from us at increasing speeds. For galaxies beyond a certain distance, approximately 14 billion light-years, the recession velocity already exceeds the speed of light, not because the galaxies themselves are moving faster than light through space, but because the space between us and them is expanding so rapidly that the total recession rate combined exceeds c. These galaxies are causally disconnected from us. Their light will never reach us, not because of any finite travel time we might eventually overcome, but because the space between us and them is generating new distance faster than light can traverse it, and that causal horizon is shrinking. The acceleration is continuing. Every year, additional galaxies cross the threshold beyond which their light will never again reach Earth. The observable universe, the sphere of space from which we can in principle receive information, is being progressively amputated by the accelerating expansion driven by dark energy. This is an extraordinary statement. It means that future astronomers, living perhaps 1 trillion years from now in a cosmos where dark energy has had billions of additional years to work, will inhabit a universe that appears nearly empty. The Milky Way and its immediate gravitationally bound companions, the local group, will remain. Everything else will have receded beyond the cosmological horizon. The night sky of that era will contain only the stars of our own galaxy and the faint glow of a few nearby bound companions. Everything beyond that, the Virgo cluster, the Perseus cluster, the Great Wall, the hundreds of billions of galaxies we can currently catalogue, will be gone, not destroyed, not dark, simply too far away, receding too fast for their light to ever reach the observers of that future epoch. Now here's where it gets truly strange. We do not know what dark energy is. This is not a temporary gap in our knowledge, a problem on the verge of resolution. It is a foundational admission of ignorance at the centre of modern physics. Dark energy makes up approximately 68% of the total energy content of the observable universe, the dominant component by far, more than matter and radiation combined. And we do not know what it is. We do not know its origin. We do not know whether it is constant across time and space, or whether it evolves. We do not know whether it is a property of space itself or a field permeating space. We have a name for it. We have measurements of its effects. We have almost no understanding of its nature. The standard model of particle physics, the most successful predictive framework in the history of science, tested to extraordinary precision across decades of experiments, attempts to account for dark energy through quantum vacuum energy, the irreducible zero-point energy of empty space predicted by quantum mechanics. The calculation is straightforward. The result is catastrophic. The quantum vacuum energy predicted by the Standard Model as a potential dark energy candidate is larger than the observed dark energy density by a factor of approximately 10 to the power of 120. That is a 1 followed by 120 zeros. The largest discrepancy between theoretical prediction and observational measurement in the history of science, by an enormous margin. It has been called, with some understatement, the worst prediction in physics. Something is wrong. Either the quantum vacuum energy calculation is wrong, which would require a fundamental revision of quantum field theory, or dark energy is not the quantum vacuum energy, which still leaves us with the question of what it is, or there is a cancellation mechanism, some unknown physical process that reduces the quantum vacuum energy to the observed value, a mechanism that itself requires explanation and has not been identified. The darkness of the universe at its deepest level is a darkness of understanding. The most dominant component of the cosmos is unknown to us. The force driving the universe's expansion, and therefore progressively erasing our view of it, is a mystery wrapped in a measurement. But dark energy is only one component of the darkness. There is another, older, stranger, more deeply woven into the fabric of everything visible. Dark matter. The evidence for dark matter predates the discovery of dark energy by decades. It was Fritz Zwicky, a Swiss-American astronomer working at the California Institute of Technology, who first formally recognized the problem in 1933, studying the Coma cluster, a large cluster of galaxies approximately 321 million light-years from Earth in the constellation Coma Berenices. Zwicky measured the velocities of galaxies within the cluster and calculated the cluster's total mass from the luminosity of its member galaxies. Then he compared the two numbers. The galaxies were moving too fast, far too fast. At their observed velocities, the gravitational pull of all the visible matter in the cluster, all the stars, all the gas, everything that emitted light, was insufficient to hold the cluster together. The galaxies should have dispersed, flying apart under their own kinetic energy, long before Zwicky observed them, and yet they remained bound. The cluster cohered, which meant the cluster contained more mass than was visible, substantially more. Zwicky called it dunkle materie, dark matter. For decades, this result was noted but not widely accepted. It could, in principle, be explained by systematic measurement errors, by undetected gas, by non-luminous ordinary matter in various forms. The smoking gun came in the 1970s, primarily through the work of Vera Rubin and W. Kent Ford at the Carnegie Institution in Washington. Rubin and Ford were measuring the rotation curves of spiral galaxies, plotting the orbital velocities of stars and gas at different distances from the galactic center. Newtonian mechanics makes a clear prediction for what these curves should look like. In the outer regions of a galaxy, where most of the visible mass is concentrated toward the center, orbital velocities should decline with distance. Just as the outer planets of the solar system orbit more slowly than the inner ones following Kepler's third law, the curve should fall off, it should drop. It did not drop. Across galaxy after galaxy, dozens of them, then hundreds, Rubin and Ford found that the rotation curves remained flat in the outer regions. Stars and gas in the distant outskirts of spiral galaxies orbit at roughly the same velocity as stars near the center. The velocity profile is flat, not falling, and flat velocity profiles, combined with the visible mass distribution of a galaxy, require the presence of additional, invisible mass extending well beyond the visible disk of stars, a massive extended halo of material that cannot be seen but whose gravitational effects are unmistakable. This means that every galaxy we observe, every spiral, every elliptical, every dwarf and irregular, is embedded in a vastly larger structure of dark matter. The visible galaxy is not the galaxy. It is the luminous core of a dark matter halo extending far beyond the stars, containing 3 to 5 times the mass of everything visible. The Milky Way's dark matter halo extends roughly 100,000 light-years beyond the visible disk, perhaps farther. It contains the equivalent of roughly 1 trillion solar masses of material we cannot directly detect. To put this in perspective, if you imagine the Milky Way as a glowing ember at the center of a vast invisible sphere, the ember represents perhaps 15 to 20% of the sphere's total mass. The rest, the overwhelming majority, is dark, invisible, interacting with everything around it through gravity alone, leaving no light, no radiation, no electromagnetic trace of any kind. And dark matter, like dark energy, is not understood at a fundamental level. We do not know what dark matter particles are. The leading candidates over recent decades have included weakly interacting massive particles, or WIMPs, hypothetical particles predicted by supersymmetric extensions of the Standard Model, and axions, originally proposed to solve a different problem in particle physics entirely. Decades of extraordinarily sensitive experiments have searched for WIMPs, underground detectors shielded from cosmic rays by kilometers of rock, large liquid xenon detectors cooled to near absolute zero, particle accelerators seeking their signatures in collision debris. No confirmed detection. No WIMP has ever been directly observed. The Lux Zeppelin experiment, operating in the Sanford Underground Research Facility in the Black Hills of South Dakota, 1.5 kilometers beneath the surface in a former gold mine, is among the most sensitive WIMP detectors ever built, using 10 metric tons of liquid xenon cooled to approximately -100 degrees Celsius. It has run for years without a confirmed dark matter signal, not a null result that disproves WIMPs entirely, but a constraint that eliminates large regions of the parameter space where WIMPs were predicted to exist. Axion searches are similarly ongoing. The Axion Dark Matter Experiment, or ADMX, at the University of Washington uses a powerful magnetic field and a microwave cavity resonator to search for the faint radio signal that axions would produce if they converted to photons in the presence of a strong magnetic field. So far, no confirmed detection. The universe is 27% dark matter and 68% dark energy. The ordinary matter, stars, gas, dust, planets, everything that has ever been seen or touched or measured in a laboratory, constitutes approximately 5% of the total energy content of the cosmos. 95% of everything that exists is unknown to us in nature, invisible to us in practice, and detectable only through its gravitational effects on the 5% we can see. The implications of this discovery are almost too vast to comprehend. We are not merely ignorant of the universe's components in some peripheral sense. The universe is dominated by things we do not understand. The cosmos, as we experience it with our instruments and our theories, is a thin, luminous film stretched over an ocean of darkness that we can measure but cannot explain. But dark energy and dark matter, profound as they are, represent the darkness of composition, the darkness of what the universe is made of. There is another darkness, different in character and more visceral in its implications, that operates at a different level entirely. It is the darkness of fate. To understand what the universe is becoming, where the darkness is leading, we need to follow the thermodynamic arrow of time forward into the deep future, through epochs so remote that the numbers describing them strain every intuitive framework we possess. The current age of the universe is approximately 13.8 billion years. The Sun has roughly 5 billion years remaining before it expands into a red giant and renders Earth uninhabitable. These are the numbers that feel relevant to human experience. The timescales on which stars form and die, on which civilizations could in principle rise and fall, on which the familiar features of the cosmos persist. But the universe's story does not end there. It does not end anywhere close to there. Consider the concept of stellar time. Stars form from molecular clouds of gas and dust when density perturbations cause regions to collapse under their own gravity. This process requires raw material, clouds of hydrogen and helium laced with traces of heavier elements. The galaxies of the universe contain reservoirs of this raw material, and new stars are forming constantly from it. But the reservoir is not infinite. Stars consume hydrogen. When they die, as white dwarfs, as neutron stars, as black holes, they lock away their mass in forms that cannot easily be recycled into new star formation. The rate of star formation in the universe peaked approximately 10 billion years ago and has been declining ever since. The universe is, right now, past its most productive era. More than 90% of all the stars that will ever exist in the history of the cosmos have already been born. We live in the declining phase, the long, slow twilight of stellar formation. In approximately 100 trillion years, 10 to the 14th power years, the last stars will burn out. The smallest red dwarf stars, the most frugal consumers of their hydrogen fuel, will finally exhaust their reserves and cool to invisibility. The universe will transition from the stelliferous era, the age of stars, into the degenerate era, a cosmos of cold remnants, white dwarfs, neutron stars and black holes, drifting through a dark, expanding void. No new light, no new energy, just the cooling embers of a stellar generation that has run its course. This progression was laid out in extraordinary detail by physicists Fred Adams and Gregory Laughlin in their 1999 book The 5 Ages of the Universe, a work that mapped the deep future of the cosmos with rigorous physics and a clarity that bordered on the harrowing. Their 5 epochs, the primordial era, the stelliferous era, the degenerate era, the black hole era, and the dark era, describe a universe of steadily deepening darkness, a cosmos trending toward a cold, empty, structureless void on timescales that dwarf the age of stars by factors of billions of billions. But the degenerate era is not the end. It is only a way station. Even the cold remnants of the stellar age are not permanent. Protons, the fundamental particles that make up the nuclei of atoms, the building blocks of all ordinary matter, are predicted by many extensions of the standard model of particle physics to be unstable. The proton lifetime has not been measured experimentally. It exceeds the age of the universe by an enormous factor, but current experimental lower bounds, from experiments like Super Kamiokande in Japan, constrain the proton lifetime to at least 10 to the power of 34 years for the most common decay modes. Theoretical predictions in grand unified theories range from 10 to the power of 31 to 10 to the power of 36 years, depending on the specific model. If protons decay, and the preponderance of theoretical evidence from extensions of the standard model suggests they do, then on a timescale of roughly 10 to the power of 40 years, all the white dwarfs and neutron stars that survived the degenerate era will slowly dissolve. Their constituent protons will decay into positrons and pions and photons, and the solid remnants of stellar death will evaporate into a diffuse haze of elementary particles. The universe will have no solid matter left, not compressed matter, not cold matter, no matter at all in any form that persists, only black holes. And black holes, as Stephen Hawking demonstrated theoretically in 1974, are also not permanent. Hawking radiation, the quantum mechanical process by which black holes slowly lose mass by emitting thermal radiation from their event horizons, causes black holes to evaporate over timescales that depend on their mass. A stellar mass black hole of a few solar masses evaporates in approximately 10 to the power of 67 years. A supermassive black hole of 10 billion solar masses, the kind found at the centers of the largest galaxies, evaporates in approximately 10 to the 100th power years. On that timescale, 10 to the 100th power years, even the largest black holes in the universe will have evaporated completely. Every black hole, from the smallest to the most supermassive, will have radiated away its mass in a final burst of Hawking radiation and dissolved into a faint spray of particles and photons. After this, after all the stars have died, after all the white dwarfs and neutron stars have evaporated, after all the black holes have evaporated, the universe enters what Adams and Laughlin call the dark era, a universe with no stars, no planets, no atoms, no black holes, an expanding void of photons at near absolute zero temperature, a handful of positrons and electrons wandering through infinite space, occasionally annihilating in brief flashes of gamma radiation that propagate outward into the darkness and are never absorbed by anything because there is nothing left to absorb them. This is the destination. Not a dramatic collapse, not a fiery ending, a slow, cold, irrevocable dispersal into meaninglessness. And the timeline of this dispersal, measured from the Big Bang to the last Hawking radiation of the last black hole, is not 14 billion years, it is 10 to the 100th power years. A number so large that the current age of the universe, 13.8 billion years, is less than a rounding error. We are not in the middle of the universe's story. We are in the first fraction of a second of the first chapter of the first page of a book that has not yet truly begun. This is what physicists call the heat death of the universe, the thermodynamic endpoint predicted by the second law, the law that the total entropy, the total disorder, of any closed system tends to increase over time. In an expanding universe with a finite total energy content and the second law operating consistently across all of time. The endpoint is thermodynamic equilibrium, a state of maximum entropy, maximum disorder, uniform temperature, with no gradients, no structures, no information, no complexity. Nothing. Some might wonder whether this is simply the most pessimistic interpretation of the physics, whether there are alternatives, loopholes, mechanisms that might redirect the cosmic trajectory away from this final darkness. There are proposed alternatives. Some cosmological models include cycles, a big crunch followed by a new Big Bang, an eternal recurrence of expansion and collapse. But current measurements of dark energy strongly favour continued, accelerating expansion rather than eventual recollapse. The universe's expansion is not decelerating toward a future crunch, it is accelerating away from one. Other proposals involve quantum fluctuations in the far future vacuum, the possibility that, on timescales of 10 to the power of 10 to the power of 56 years or more, thermal fluctuations in the quantum vacuum could spontaneously assemble local patches of order out of the disorder, producing what physicist Ludwig Boltzmann first imagined and what cosmologists now call Boltzmann brains. Spontaneously assembled observers appearing briefly in an otherwise dead universe before dissolving back into equilibrium. These are real proposals with real physics behind them, but they describe phenomena so sparse, so temporary, so isolated in an otherwise featureless void that they offer little comfort. Let us step back from the deep future and return to the present, because there is a darkness of the present, quantifiable, measurable, observed, that deserves direct confrontation. In 2021, a team of researchers led by Mark Postman at the Space Telescope Science Institute and Todd Lauer at the National Optical Astronomy Observatory published results using data from the New Horizons spacecraft, the probe that flew past Pluto in July 2015 and has since been travelling outward into the Kuiper Belt and beyond, currently more than 5 billion miles from Earth. New Horizons is far from the inner solar system, far from the scattered light of planets and zodiacal dust that can contaminate observations made closer to the Sun. Its position makes it uniquely suited for measuring the actual optical background brightness of the universe. The total amount of visible light arriving from all directions, stripped of local contamination. What Postman, Lauer, and their colleagues found in the New Horizons data was a residual background brightness, a glow of optical photons arriving uniformly from all directions, that was approximately twice as bright as could be accounted for by all the known sources in the observable universe. All the galaxies, all the quasars, all the diffuse light from stellar halos and intracluster medium, added together, they produce only about half the light actually measured. The other half is unaccounted for, its source is unknown. In 2022, a separate analysis using a different methodology, combining data from New Horizons with measurements from the Hubble Space Telescope's deep field observations, confirmed the excess. The universe contains roughly twice as much optical light as its known contents should produce. Something is generating photons that we cannot attribute to any catalogued source. Proposed explanations include decaying dark matter particles that release photons as they decay, a process that would be consistent with dark matter being an unstable particle with a very long lifetime. Another proposal involves axion photon conversion, dark matter axions converting to photons in the presence of intergalactic magnetic fields. A third possibility is a population of sources so distant, so faint or so unusual that they have escaped detection even in the deeper surveys, ultra-faint dwarf galaxies, intracluster stars, or exotic objects not yet identified. None of these explanations is confirmed. The source of the excess optical background remains unknown. Even the darkness, it turns out, contains secrets. But this raises an even bigger question, and it is perhaps the most important question that the darkness of the universe forces us to confront. If the universe is trending toward maximum entropy, if the thermodynamic arrow of time points relentlessly toward dispersal and equilibrium, then the existence of structure, of complexity, of stars and galaxies and planets and life is not the normal condition of the universe. It is an anomaly, a temporary deviation from equilibrium, a local, improbable fluctuation in a cosmos whose default state is darkness and disorder. The galaxies we observe, the stars that light them, the planets that orbit those stars, the biospheres that have emerged on at least one of those planets, All of this represents a vanishingly small fraction of the universe's total energy budget, and an even more vanishingly small fraction of the universe's total timeline. We exist in a sliver of cosmic history so brief, so extraordinary, so improbable in the context of the universe's deep future, that the concept of luck barely does it justice. Why is the universe structured? Why does matter clump into galaxies and stars rather than dispersing uniformly through space? Why did the Big Bang produce conditions that allowed complexity to emerge rather than conditions of maximum entropy immediately? The answer involves the initial conditions of the Big Bang itself, and the extraordinary degree to which those conditions were fine-tuned, or appear to be fine-tuned, for the emergence of structure. The second law of thermodynamics tells us that entropy increases, but for entropy to increase, it must start low. The Big Bang produced a universe of extraordinarily low entropy, not because it was smooth and uniform, which high entropy would actually resemble, but because it was smooth and uniform in a gravitational sense. Gravity changes the rules. When gravity is included in the thermodynamic accounting, a uniform distribution of matter is actually a low entropy state. Clumped, structured matter, stars, black holes, galaxy clusters, represents higher entropy. The universe began in a gravitationally low entropy state, and has been increasing its entropy ever since by forming structures. This is Roger Penrose's argument, developed in his work on the Big Bang's initial conditions, particularly in his 2004 book The Road to Reality. Penrose calculates that the low entropy initial conditions of the Big Bang are so improbable, so extraordinarily fine-tuned, that the probability of a universe like ours arising by chance is approximately 1 in 10 to the power of 10 to the power of 123. A number so vast that writing it out in standard notation would require more digits than there are atoms in the observable universe. This calculation is not universally accepted. It depends on specific assumptions about the measure on the space of possible initial conditions, but it captures something real about the extraordinary specialness of the universe we inhabit. A randomly selected state of a universe with our total energy content would not look like ours. It would be formless, structureless, already at maximum entropy, already dark in every sense, and yet here we are, in a universe of galaxies and stars and complexity, with eyes to see them, with minds to ask why. Does the darkness of the universe's deep future make the present moment less meaningful? Does the knowledge that every star will die, every structure will disperse, every complexity will dissolve into equilibrium, does that knowledge constitute a kind of cosmic nihilism, a reason for despair at the larger scales? There is a serious philosophical tradition that says no, and the argument is not merely consolatory, it is grounded in the physics. The universe's low entropy beginning is the source of everything valuable in the cosmos. Every star that shines does so because it sits in a gravitational potential, burning fuel toward equilibrium. Every chemical reaction, every metabolic process, every neural firing in every brain that has ever thought about these questions, all of it is powered by the gradient between low and high entropy, by the thermodynamic arrow that points from order toward disorder. The darkness of the future is not a threat to the meaning of the present. It is the engine of the present. The universe is doing something with its low entropy. It is building complexity. It is generating information. It is, on at least one small pale planet orbiting an unremarkable star in an ordinary galaxy, producing minds that can contemplate the very darkness toward which everything is tending. Carlo Rovelli, the Italian theoretical physicist and author of 7 brief lessons on physics, articulates a version of this perspective with characteristic clarity. The beauty of the universe is not diminished by its finite duration. The finite duration is what makes the universe dynamic, creative, structured, rather than the static equilibrium of maximum entropy. The darkness ahead is the price of the light we currently inhabit. But this philosophical consolation does not resolve the scientific questions, and the scientific questions about the universe's darkness are advancing rapidly. The European Space Agency's Euclid telescope, launched in July 2023, is conducting a survey of the large-scale structure of the universe covering more than 1/3 of the entire sky, imaging billions of galaxies across 10 billion years of cosmic history. Euclid's primary science goals are the characterization of dark energy and dark matter, mapping the distribution of dark matter through its gravitational lensing effects on background galaxies, and measuring the rate of the universe's expansion across cosmic time to constrain the properties of dark energy. Early Euclid results, released in 2024, demonstrated the mission's extraordinary capability for weak gravitational lensing measurements, the subtle distortions in the shapes of background galaxies produced by intervening dark matter concentrations. These measurements are being used to build three-dimensional maps of dark matter distribution that extend across cosmic scales, providing the most detailed picture yet of the invisible scaffolding on which the visible universe is hung. The Nancy Grace Roman Space Telescope, NASA's planned Wide-Field Infrared Survey telescope scheduled for launch in the mid-2020s, will complement Euclid's dark energy survey with additional measurements of Type 1a supernovae and baryon acoustic oscillations. The regular spacing in the distribution of galaxies that acts as a cosmic ruler for measuring cosmic distances and expansion rates. Together, Euclid and Roman will provide constraints on dark energy that are orders of magnitude more precise than current measurements. Will those constraints tell us what dark energy is? That depends on what dark energy is. If it is a perfectly constant cosmological constant, the same in all times and all places, then even the most precise measurements of its effects will not reveal its mechanism. They will only confirm its constancy. If, on the other hand, dark energy varies across time or space, if it has dynamics, if it evolves, then Euclid and Roman measurements will detect that evolution, providing the first hint of dark energy's physical nature rather than merely its observed consequences. Recent results from the Dark Energy Spectroscopic Instrument, or DESI, a multi-fiber spectrograph installed on the Male 4-meter telescope at Kitt Peak National Observatory in Arizona, added a provocative twist to this question. DESY's first year of data, released in April 2024, produced the most precise measurement yet of the universe's expansion history using baryon acoustic oscillations. The data, while broadly consistent with standard cosmology, showed hints, at roughly 2 to 3 sigma statistical significance, of dark energy that is not constant. Dark energy that may have varied over cosmic time. An evolving dark energy would be a profound discovery, implying that dark energy is not simply a property of space, but a dynamic field that changes with cosmic history. 2 to 3 sigma is not a confirmed discovery. It is a hint, a statistical fluctuation that could be noise, could be systematic error, or could be the first signal of something genuinely new. The physics community is watching the DESI data carefully as additional years of observation accumulate, and the statistical significance either grows or fades. This is what science looks like at the frontier. Not certainty, not clean answers, a hint at 2 sigma, a measurement that agrees with expectation except for a nagging residual, a background brightness that doesn't quite balance. The darkness of the universe is not merely physical, it is epistemic, a darkness of not yet knowing that is, in its own way, as vast as the physical darkness between the galaxies, and that epistemic darkness is not a failure. It is a location on a map, a marker on the boundary of what is understood, pointing toward what is not. Every great discovery in the history of cosmology, the expansion of the universe, the Big Bang, dark matter, dark energy, the cosmic microwave background, began as an anomaly, a measurement that didn't quite fit, a number that was wrong by a factor of 2, or a factor of 100, or a factor of 10 to the power of 120. The darkness of the universe has been the source of every major cosmological revolution of the past century. There is no reason to think it has finished yielding its secrets. We began with a simple observation. The night sky is dark, and we have followed that darkness. Through Olber's paradox and the expanding universe, through dark matter and dark energy, through the thermodynamic destiny of a cosmos trending toward maximum entropy, through the measured excess of light that no known source can explain, to a place that is both humbling and, in a strange way, clarifying. The universe is dark for reasons that are profound, interconnected, and not yet fully understood. It is dark because it had a beginning, and light from before that beginning cannot reach us. It is dark because the expansion of space drains photons of their energy before they arrive, shifting light beyond visibility. It is dark because 95% of everything that exists, dark matter and dark energy, neither emits nor interacts with light in any form we can currently detect. It is dark because the thermodynamic arrow of time points toward a future of dispersal and equilibrium that will eventually extinguish every light in the cosmos. And it is dark, perhaps most profoundly, because we do not yet understand it fully, because the numbers don't quite add up, because dark energy defies calculation, because an excess of optical light hovers in our measurements without a confirmed source. The darkness is not just a physical fact, it is an invitation. Every instrument we have launched, Hubble, Chandra, the Cosmic Microwave Background Satellites WMAP, and Planck New Horizons, Euclid, has pushed the boundary of what we know about the cosmos's darkness and found, at every boundary, something new that we did not know was there. One thread remains unresolved, and it is the one that matters most. We do not know what dark energy is. We do not know what dark matter is. And these are not peripheral mysteries. They are the dominant realities of the universe we inhabit. 95% of the cosmos is unknown to us at the level of fundamental physics. The darkness we observe is not the whole darkness. It is the visible edge of a deeper obscurity that our current theories cannot illuminate. That is not a comfortable place to sit. It is, however, an extraordinary one, because we are the first generation of minds, on this planet at least, with instruments sensitive enough to measure the darkness precisely. To map dark matter halos, to detect dark energy's acceleration, to hear the microwave whisper of the Big Bang's afterglow, to notice that the light doesn't add up and ask why. The darkness is vast. It is ancient. It is, in all probability, deeper than anything we have yet encountered, and we are only beginning to look.